Yeah, I'm talking about prefrontal cortex, which is quite unusual. Normally, I talk about visual cortex, not prefrontal cortex. So some people in the audience are like, what are you going to talk about? But I first want to thank actually the people that did most of what I'm going to talk about. Xiaolian Qi and Qi Zhu at Nurspan. Xiaolian still in my lab, almost finishing her PhD. And I also want to make some PR for the monkey people here. We have a new template, a monkey template based on 10 individuals with high resolution T1, T2, CT images, which are available. I think these QR codes should be working by now. So if you're interested, test it out or contact me afterwards. So that's new. And actually, Nicola, who is around, has been working very hard together with some people from the lab to get this going. Prefrontal cortex. I must say that I very much liked the talk of Henry, who admitted that he was wrong at some point in his career. I commend Henry for doing that, and basically saying that a single area should not be looked at as a single point. Henry is sort of like trying to make the case that we should look at gradients, eccentricity gradients, to add another dimension. Actually, I would like to give my take-home message now. I don't think that's even enough. I think it's at much finer scale, basically, that we have to look at things. So just adding gradients is probably not enough. So, Henry, sorry that I have to say, but you may have to admit within 10 years down the road that you have to go to another finer scale. So, prefrontal cortex, by and large, standard view is that it's consisting of different areas. Everybody knows this is just like lateral prefrontal cortex. A bunch of areas. 46, area 46 is a big occupier of that territory, cortical territory. Also 45, 47, 10. On top of that, also exactly as Henry was talking about in visual cortex, when he was talking about visual cortex, people have been describing these gradients, like spatial selectivity gradients from the back of dorsal lateral prefrontal cortex, fading basically towards the frontal pole. The same thing for object selectivity, the gradient more ventrally in dorsolateral prefrontal cortex. But I think there is quite a bit of anatomical evidence that there are mesoscale structures also in prefrontal cortex. And I want to keep it light and short because of the post-lunch time. Everybody is dozing in. I think Goldman-Rashkish was probably amongst the first to show it, making injections in different layers in different areas of prefrontal cortex and revealing basically columnar-like structures, very similar to what people have been seeing at that time in posterior occipital visual areas. I think about the work of Hubel and Wiesel, or even parietal cortex, the work of Mountcastle, and so on and so on. So there is quite a bit of evidence that you do have these very small structures in prefrontal cortex of primates. Also nice work more recently from the Parma group, basically, when they are injecting in one spot in prefrontal cortex, you start to see glimpses here of like these patterns of connected areas, very small connected areas in the frontal lobe. Again, indicating that there might be some mesoscale structure in frontal cortex of macaques. I think very beautiful work. It's not, as far as I know, not published yet. Injections from a Japanese group, Watakabe et al. Is on bioRxiv. They made injections, and then they made basically both injections with retro and anterograde traces, and they beautifully see these columnar-like structures, and they see an overlap between retrogradely labeled neurons and axon terminals, sort of like indicating sort of like an overlap cortical circuitry in frontal cortex, basically, where these different types of connections are really converging. So sort of like really telling there is a microcircuitry of mesoscale anatomical structures, connectional structures in this case. Another example here, optical imaging, 2008. Same thing, basically. They are microstimulating somewhere in prefrontal cortex, and they see columnar-like structures with optical imaging, in this case here in the principal sulcus. However, functional evidence is merely lacking. There's not a lot of evidence. I was very surprised when we know all about these anatomical fine-scaled structures that there is very little functional evidence for mesoscale or columnar-like entities in prefrontal cortex. Actually, Christos mentioned that. There is some electrophysiological evidence that points to it, but not really in detail. And that's where I think imaging, high-resolution functional imaging, comes into play. And we developed methods, basically, where we have coils implanted on the skull of the animal, which improves our sensitivity by basically a log unit relative to when you're using external coils, which can be implemented or supplemented with access ports to the cortex to do follow-up electrophysiology experiments, basically with the same animal. So you can do very fine functional imaging and then go after these functional imaging patches, basically, to see what the neurons are doing or inactivate these patches. So, are there small functional patches in prefrontal cortex of a macaque monkey? And we started looking at that even using very low-level visual features. You do not expect that this is sort of like a defining feature of prefrontal cortex, but we did it anyway because we were mainly interested in the back of the cortex. But because of the symposium title, I don't talk at all about the back of the cortex, only about frontal cortex. And I hope it is visible. Here I show some examples where we showed random dot patterns, big random dot patterns, just dots that were moving and that were either rotating or expanding, sort of like typical optic flow stimuli used to look at functional properties of motion areas, MST, FST, LIP, and so forth, and so forth. And you see here, and this is in premotor cortex here, you see these blue and red dots here, also near the arcuate sulcus. You see nearby different functional entities. I would never believe this was true because the thresholds are relatively liberal. You do this the next day and you see basically these very tiny little functionally segregated entities in this part of frontal cortex, not prefrontal cortex. Another example, again, low-level disparity. Just looking at the depth-defining stimulus versus monocular control. This is really prefrontal cortex. I would never have believed that. You see these very tiny little structures, very segregated, very reproducible structures in prefrontal cortex. Why would that have to be there? Another one, slightly more complex. Everybody knows that. Faces. Faces versus objects. People have been using that very often to identify category-selective regions in the back of the cortex, face-selective regions in the back of the cortex. Look at this granularity, basically, when you do this kind of contrast using high-resolution fMRI. This is like with voxels of 0.6 millimeter resolution, isotropic resolution. You see these very, very small structures basically being activated selectively for monkey faces relative to monkey objects. So a bunch of low levels visual features basically driving small compartments in prefrontal cortex. Scenes, a little bit more complex. Is there selectivity at this scale in prefrontal cortex? Yes, indeed. This is data from 2 animals. Now you see these very tiny little dots, more or less resembling what you see, what I showed you in the beginning with the anatomical tracer connections, where you saw traces coming in nearby segregated regions. You see these very dotted-like pattern, highly selective, highly reproducible across different stimuli, across different monkeys here in prefrontal cortex. That's function. Are these things connected? Ideally, you would like to do something that Henry was doing. You know, going into these patches and injecting these areas. This would be very interesting to do. We have not done that yet. So the poor man's solution is to look at functional connectivity by acquiring resting state fMRI data and the same animals, and then see, do these networks of, let's say, category selective patches, the one versus the other, do they have different connectivity patterns? And we did that for the scene patches, for example, and actually also for the body and face selective patches. And indeed, when you do that, then you see that patches, even across large distances from frontal cortex to occipital-parietal cortex, that these scene patches show a higher degree of resting state functional connectivity than, for example, a scene patch with a nearby body patch. So there are at least partially segregated functional mesoscale networks. This is for bodies. We see the same thing for when you do the comparison between scene mesoscale functional networks and face mesoscale functional networks. This is fMRI. What does fMRI tell us? Not much, right? It's a hemodynamic, very slow signal, so you have to get in basically with an electrode to see what these things are doing, and that's exactly what we started to do. Of course, this is very laborious. These are very laborious experiments because you really have to go there, target it, and so on, and so on. And again, there is a PhD student in my lab who started doing that, and she is also involved in that for quite a few years now, where we targeted now face selective mesoscale patches in frontal cortex, and again, very reproducible. Again, one day of scanning, the other day of scanning, and you see very, very highly reproducible patterns. The whole idea is to go there with electrodes in several of these patches, not just one of these patches. And I just want to give you an example here. 4 different patches, and actually also one in infratemporal cortex, anterior infratemporal cortex, as sort of like comparison, because like most people who have been doing these kind of experiments have been recording in a string of face selective patches in infratemporal cortex, the anterior medial face patch to be more precise. And you see here the responses for different stimulus categories. Faces, these are objects, birds, bodies, and all kinds of objects. And you see that in all these face patches, indeed, defined by the fMRI, that we do find a great deal of face selectivity at a single neuron level. Moreover, something that you cannot derive with functional imaging, but fMRI basically is, of course, temporal information. And you see that indeed these different areas, these are just like example neurons, that they do have different temporal profiles. This one basically is very selective for faces, both monkey and human faces, barely anything for any other of these stimulus categories. And the response is relatively long-lasting, while in some of the other areas you basically see a very short transitional response. Compared to this infratemporal face patch, more or less the same kind of answer as what you see here in this orbitofrontal small face selective unit or domain. You can then compare also selectivities, and quite surprising to us, basically, we see that here in purple, this is the response in an area where we recorded from all these areas, from all these different face selective patches in IT, which is slower than some of these frontal patches, which means that the traditional view that information passes from infratemporal cortex to frontal cortex is not entirely true, and that there are probably several parallel pathways in sending this kind of face information to both infratemporal, anterior infratemporal, and a frontal cortex. So probably evidence for multiple parallel face processing channels. So just a very quick overview of a few of the data that we have, which makes me wonder, and this is sort of like in addition to what Henry was saying, do we need a new model of functional architecture of neocortex, prefrontal cortex? The traditional view is sort of like what Henry said. You have different areas. You have like feed-forward connections, feedback connections, and lateral connections. More or less, and I should have picked up a slide from Henry's lab, but more or less inspired by what we know for decades, sort of like the Velleman-Van Essen diagram with this very, very dense connectivity pattern. But this is exactly as Henry said, looking or describing areas as one single point. Yeah. We know actually that in early visual cortex that's not the case. We know that in early visual cortex small subunits are forming parallel mesoscale functional networks between different areas, also within areas. So they are really segregated, well, to a large degree segregated functional pathways that's sending very specific information, for example, from the blobs, let's say color information from blobs to thin stripes in area V2 to globs, color selective modules in area V4. And these things are also connected. Let's say this is like one mesoscale functional domain, there's another one, they're also interconnected within bigger areas. And actually this carries much more information than the areas on its own. Color is relatively well segregated from motion processing and so forth and so forth. So the question arises whether this holds true for the rest of the cortex, whether that kind of information, of course, there are additional changes that will happen at different hierarchical levels, but whether these mesoscale kind of networks keep there or remain there throughout the cortex up to prefrontal cortex. So remember that we see for very low level visual features these kind of small domains in visual cortex. This is an open question, and this is, I'm not saying this like that, this is an open question. So then you can wonder whether these aerials definition really makes sense for understanding function of the neocortex. Maybe it's just these networks of small mesoscale functional domains that matter more than areas. So we see definitely, or we do definitely have evidence for anatomical mesoscale units in prefrontal cortex. They are functionally relevant. We see very, very clear functional differences between different mesoscale domains. To some extent, and I know this is very poor man's solution, they are functionally connected. I think resting state functional connectivity, if you would have the sensitivity, you can derive it, but you need other methods to make sure that these domains are anatomically connected, sort of like pointing into the direction whether or not we need a very new model actually of functional architecture for prefrontal cortex or for neocortex in general for primates. So I want to come back to what Timo was pointing out this morning. What's next? What do we need to know? What is actually the alphabet? Why are these things sitting there? I think it's a very important question to address. And what do we know? What do we need for it? We need a connectome. I think having the connectivity, but at a very, very detailed scale is very, very important. I'm not sure we have the technology to do that at this very moment. So knowing basically almost all the courses of all the axons of a primate brain. I don't think we are capable of doing that. Also very important, I showed you some electrophysiological fMRI targeted recording. You want to do that simultaneously in as many of these patches together. Of course, technologically not easy. We're getting there, we are slowly getting there, but I think it's very crucial to understand how information flows through these different mesoscale functional units. Of course, another thing is like, does this hold true for the human? Do we see the same kind of things in the human? I think right now we don't know. Simply because we are very much biased by low resolution fMRI data in humans and by piling data from different subjects in one big pile where you lose this detail information. You really have to do very, very high resolution, high sensitive imaging in single subjects to figure this out. And I think we are almost about to start doing that. Another big question is like, how does this relate to perception and behavior, right? Are these things really relevant to understand cognition? We do not know. To do that, I think we have to start using tasks. Whatever I showed was just passive stimulation. You need to have, you need to start doing cognitive tasks and see whether you get sort of like similar kind of mesoscale functional networks, domains, basically in prefrontal cortex and in the rest of the cortex. Of course, then you have to start interfering, also not trivial, because you have to do it at very small scale. It's not knocking out a complete area, not flooding it with mucimol or with TMS or whatever else. You really have to get to very detailed structures, non-trivial at all. But again, I think we are almost there to start doing that. Also, another very interesting question is like, how do these things differ across different individuals? And does it explain differences in behavior, differences in perception, differences in cognitive abilities? The big elephant in the room to me is also how these smaller scale entities, functional entities, anatomical entities, how they do relate, to the bigger maps. Because we know, and now I'm going back to visual cortex, we know that there are maps. What's the relation between these bigger maps? Maybe these bigger maps provide just the receptor information, the map of the receptors basically, retinotopic maps, somatotopic maps, and so on and so on. And that these things are just embedded in that, and that you need to have like both types of information. Finally, I think having genetic information about that, and that's where I want to get back to what was said this morning, would be highly interesting information. Thank you.